Welcome to this video on measures to validate diagnostic test. In diagnostics, it is not enough for a test to simply give a result. We need to know how reliable, accurate and useful that result really is. In this section, we will quickly walk through the essential metrics that determine a test performance, including sensitivity, specificity, predictive values, and overall accuracy tools like ROC curves and AUC. These measures help us decide whether a diagnostic test can truly guide clinical and scientific decision making. Let's get started. Before we go into the details of how diagnostic tests are evaluated, it is important to understand a few key concepts that form the foundation of test validation. First, we talk about incidence and prevalence. Incidents tell us how many new cases occur in a population over a period of time, while the prevalence tell us how many existing cases are present at a given moment. It includes both the new and the old cases. These two measures help us understand disease burden and they influence how useful a test will be in real-world settings. Next, we look into the performance characteristic of a test. That's the sensitivity and the specificity. Sensitivity, the ability of a test to correctly identify those who have the disease, and specificity, the ability to correctly identify those who do not have the disease. From these, we derive two very practical measures, negative predictive value and the positive predictive value. And the positive predictive value tell us how likely a positive test result truly represents the disease, and the negative predictive value tell us how likely a negative result is truly disease-free. Both depend heavily on the prevalence of the disease in the population. We also use Bayes' rule, which help us understand how pretest probability modify the interpretation of a test result. Finally, we evaluate the overall diagnostic accuracy using tools like the receiver operating characteristic curve or ROC and the area under the curve, the AUC, which summarize how well a test discriminates between diseased and the non-diseased individuals. Before validating any diagnostic test, we need to understand the disease frequency in a population because it directly affects how useful the test will be. We will study the incidence taking an example of a disease X in a population. So, incidence refers to number of new cases that develop in a population over a specific period of time. It tells us how fast a disease is occurring. For example, there is 7 new cases of a disease appearing in a population of 10 people over 1 month. So, the incidence of the disease in this population is 70%. Prevalence, on the other hand, tell us the total number of existing cases that include both the new and the old at a particular point of time. It shows us the overall burden of the disease. For instance, if 20 animals in a herd of 100 currently have the disease, then the prevalence is 20%. Now we need a test which can identify this disease. So we developed a test, rapid test X. When we evaluate this test, there are a few essential questions we must ask before trusting its result. First, is the test good? This means, does it reliably tell us who truly has the disease and who does not? Then we ask, how can we measure the quality of our test? To answer this, we look at key performance indicators such as sensitivity, specificity, predictive values and overall accuracy. Another important question is, can this test identify all the positive cases? This relates directly to sensitivity, the test ability to detect true positive and avoid missing infected individuals. Next, we consider the purpose of the test. Is the test suitable as a screening test or should it be used as a confirmatory test? A good screening test needs high sensitivity, so we don't miss cases, whereas confirmatory tests require high specificity to avoid false positive. Finally, we compare it with the existing alternatives. Is our test better than rapid high test X or not? To evaluate this, we look at the ROC curves, AUC values and head-to-head performance metrics across different prevalence settings. These questions guide us entire validation process and help us determine whether a test is truly reliable and fit for clinical or field use. Again, coming back to the disease scene, in this population of 10 people, 7 is actually having disease and 3 are healthy. But our test came as 9 having disease and 1 is negative. So, few values we can derive from this population. First one is true positive, that is 7. These patients truly had the disease and our test correctly identified them. The next is false positive, which means this patient did not have the disease but the test showed a positive test result. Next is false negative, that is 0. No deceased patients were missed by the test. Next is true negative, that is 1. One patient without disease was correctly identified as negative by the test. Now we are confused about whether our test is really a good or bad product because some of the results were not good. Now let's interpret this. For that we have to write the result on a table of 2 into 2 matrix in which disease on this side and the test on this side, and we will get the values of true positive, false negative and true negative. First we look into the sensitivity. The sensitivity will tell us how well the test identify people who actually have the disease. How we will calculate the sensitivity? There is an equation, that is true positive divided by all deceased. So here all deceased is true positive plus false negative. What's the value here? It is 7 divided by 7 plus 0, that is 7. 7 by 7 equal to 1, that is equal to 100%. So our test is excellent at detecting positive cases. It did not miss a single deceased person. Next we look into the specificity. Specificity will tell us how well the test identify people who do not have the disease. The equation for specificity is true negative divided by all healthy, that is true negative plus false positive. So how we will calculate? Here true negative is 1. 1 divided by true negative plus false positive, that is 1 plus 2, that is 3. 1 by 3, that is equal to 33%. This means our test is poor at ruling out disease and give more false positive. So now we face the question, is our test good or bad? The answer is, it depends on how we plan to use it. Because of its high sensitivity, our test is very good at screening tool. It catches all true cases. But because of the low specificity, it is not suitable as a confirmatory test. It mislabels healthy people as positive. This explains why some of our tests looks not good. Our test is strong in detecting disease but weak in confirming it. To improve it, we need to work on reducing false positive, which will increase specificity. Now we will derive the value for the positive predictive value and negative predictive value. So first we will learn about positive predictive value. Positive predictive value is how often is a deceased person picked up positive by our test. How we will calculate this? It is true positive divided by true positive plus false positive. And next is negative predictive value. It is how often a healthy person tested negative in test. How we will calculate this? It is true negative divided by true negative plus false negative. Again, the sensitivity, how we will calculate, it is true positive divided by true positive plus false negative. 7 divided by 7 plus 0, that is equal to 100%. Next is specificity, that is true negative divided by true negative plus false positive. 1 divided by 1 plus 2, that is equal to 33.3%. Next is positive predictive value, that is true positive divided by true positive plus false positive. 7 divided by 7 plus 2, that is equal to 77.7%. Next is negative predictive value, that is true negative. 1 divided by true negative plus false negative, that is equal to 100%. Here the positive predictive value and the negative predictive value dependent on the prevalence of the disease, whereas the sensitivity and the specificity will not be altered with change in prevalence of the disease. There is another equation where we can calculate the predictive value using the prevalence. So positive predictive value equal to sensitivity into prevalence divided by sensitivity into prevalence plus 1 minus specificity into 1 minus prevalence. And negative predictive value we can calculate it by specificity into 1 minus prevalence divided by 1 minus sensitivity into prevalence plus specificity into 1 minus prevalence. So we can calculate predictive value when prevalence, sensitivity and specificity are given. Now we will look into the result of another test, that is rapid height test X on the same population. By this test, it is showing 6 true positives and 1 false negative, 0 false positive and 3 true negative. So we will now derive its sensitivity, specificity, positive predictive value and negative predictive value. Now we will calculate the sensitivity, specificity, positive predictive value, negative predictive value for the second test. So equation for the sensitivity is true positive divided by true positive plus false negative. So true positive is 6, 6 divided by 6 plus 1, that is equal to 85.7%. Next is specificity. How we will calculate this? Specificity is equal to true negative divided by true negative plus false positive, that is equal to 3 divided by 3 plus 0, that is equal to 100%. Next is positive predictive value. How we will calculate the positive predictive value? That is equal to true positive divided by true positive plus false positive, that is 6 divided by 6 plus 0, that is equal to 100%. Next is negative predictive value. It is true negative divided by true negative plus false negative, that is equal to 3 divided by 3 plus 1, that is equal to 75%. So our first test, rapid test X, sensitivity was 100%. So that test was a better screening test. So we have to choose the test with high sensitivity as a screening test. Next is rapid height test X. It is having high specificity. So those tests should be taken as the confirmatory test. That is, specific test will rule in the disease and the sensitivity test will rule out the disease. So now which test we have to use for screening and confirmatory? The screening test prioritize high sensitivity to capture nearly all true positive cases, which is crucial when missing a case is dangerous. False positive are acceptable here because positive are confirmed later. Confirmatory tests, on the other hand, prioritize high specificity to ensure only true positives are identified, preventing unnecessary intervention. So always go for a two-step approach. That is, test with high sensitivity used for screening and test with high specificity used for confirmation. Now we will talk about the ROC curve, AUC, that is area under the curve, and the diagnostic test performance. First we will look into the ROC curve. How we will plot this? It is having the sensitivity on the y-axis, and on the x-axis it is having false positive value or 1 minus specificity. An ROC curve plot sensitivity versus 1 minus specificity at all possible threshold, showing the trade-off between detecting true positive and avoiding false positives. And the area under the curve AUC summarize the overall test performance. Closer to 1 is better. So AUC equal to 1, that is a perfect test. AUC 0.5 means test perform no better than chance. So higher the AUC, that will have a better discriminative ability. Thanks for watching.